before we talk about the distinctions between injection, surjection, and bijection, it would be more fundamental for us to understand what a total function is versus what a partial function is. You may have known the definition already, but if you don't know, now it would be the time to really distinguish between them completely and clearly. Let's take a look. So given the relation R, which is a member of the set of possible relations between two sets, S and T, right? And we know that as long as R can satisfy a certain functional property, it will be a function. But now, what kind of function is that? We want to talk about something that's more fundamental than injective, surjective, and bijective. Let's distinguish between total versus partial. Let's see. What a partial function is. A partial function is satisfy the functional property. Oh, let's start with this. R being a relation would be a partial function, and the way we write it is by an arrow, right arrow with a forward slash around the line over there, right? I'll write it down on the paper in a moment. Okay. Number one, the relation R must be functional, right? We talked about the functional property in the earlier part of the module. You can review it if you got any doubts. And then we're saying that domain of R can be a subset of the first set S, right? This in some way is a very, very generous definition here. That's the nature of the partial function. Okay, let's see what the consequence is, and I'll give you example. So the remark here is really important. If I say R is a member of the set of possible partial functions between S and T, that means there may or may not be a domain value S such that if I try to apply S onto the function, it's undefined. By the way, you might notice some syntactical difference already. Whenever I know that if here I actually made a slight mistake over here. So since I talk about R, so this part over here should be R as well. I'll fix the slide when you download it. Okay. So if I treat R as a function, in that case I can use parentheses over here with a single value, as opposed to a set of value in the case of relational image. To really distinguish between function application versus relational image, I'll talk about it in the next slides. All right. Anyway, it's a typo here. It should be R. Okay. And in the case of partial function, we allow the possibility where the value from the domain is simply not some value from the first set over here is simply not in the domain, meaning that it may be undefined. Let's see some example. That's what the partial function allow. Okay. For example, over here, let's say we are talking about this particular partial function. It's a partial function between this set over here and also this set over here, right? And it's a partial function. And I'm using a subset relation over here. So I'm saying that this particular set, which contains two members over here. So this is function number one, which is one example of partial function. This is function number two, which is just another example of partial function. Well, just to show you how you can use the operator we have learned before to give you example. All right. So the first partial function goes like this. The first partial function is, you can see, is a function because 2 is mapped to some unique A, and 1 is mapped to some unique B. Right? It's they do not map. Each one of them does not map to more than one elements. That will be violating the functional property as we mentioned before. And if you look at the domain of this particular function, function number 1, the domain is simply 2 and 1. 2 and 1 is a subset of the first set over here. So that's a partial function. On the other hand, you can see the second set over here. You can see in that case, 2, 3, and 1 are the domain for this particular function. And 2, 3, and 1 is also a subset of that particular domain, right? To be more precise, the domain over here, 2 and 1 together, is a proper subset of this particular domain because we don't really contain, for example, 3 over here. The 3 is not part of the domain in this particular function, but that's okay because we get a subset relation, right? Hopefully you're following so far. And let me try to annotate something here just in case you have some doubts about this particular example over here. So let me just get a snapshot of this. Okay, let's now talk about some annotation. You will see this kind of format for the example very often when I give you example. Let's now clarify this very quickly. All right. So over here, if you talk about just this part over here, so this part tells you the set of possible partial functions. Between this set over here and also this set over here. All right, and this is a subset relation. So we are basically saying that this is function number 1. So this is function, and this is just another function. Both of them are members of this particular partial function. Well, they're possible partial functions basically. So this is just another function over here, right? And for this particular function over here, you can see the domain of that is actually equal to 2, 1. And the domain for this function over here is actually 2, 3, and 1. And both of them are actually subset of 1, 2, 3, right? To be more precise, this one here, not only that is a subset of that, it's also a proper subset, right? So when you say it's a subset of this set over here, it's actually true. When you say it's a proper subset of this particular set, it's also true. On the other hand, if you say this set over here is actually a subset of this set over here, that's actually true. But if you say this is a proper subset of this set over here, that's not true. All right, it's a very quick annotation just for you to see the example, right? So we're giving 2 examples essentially. This is a partial function. This is just another partial function. All right. Okay, let's now move on. And the Ascii syntax for partial function would be something like this, right? You can see this, the plus over here, somehow, well, kind of mimic the visual look of the partial function over here, like this, right? It's something you should know for the later when you use the rodent tool to enter the specification from the keyboard. So that's about a partial function. What about total function? A total function, if there's a mapping for each S that's a member of S, which means we don't really have this kind of function. This is a partial function, but that's not a total function, because you can see in this case, the domain, the value 3 from the first set in the relation is undefined in terms of this function, right? You can see 3 is not there. On the other hand, this is a total function, in which case we got 2, 3, and 1 in there. All right. So the formal definition is R is a member of the set of all possible total function if and only if, first of all, the functional property must be satisfied, that's for sure. And the domain, now we are being stricter. It must be exactly equal to S, right? So now you can see very easily that a total function is a partial function. However, a partial function is not necessarily a total function, because when we say the domain of R is equal to S, it's definitely a special case where it's a subset of S. However, if I only say the domain of R is a subset of S, it does not necessarily mean it's exactly equal to S, right? It's exactly how you can see the definition. Right, it's the remark. Well, that's exactly what I just meant, right? Let's visualize this relationship very quickly, all right? So now if you want to see the difference between total function and partial function, thinking this way, okay? So think about this one over here would be the set of total function. So S total function T over here, right? So this has the special property where the domain of, so this will be, let's say R is a member of, right? Domain of R is actually equal to S. Exactly. All right. So what about partial function? Partial function will be a strictly larger set or superset over here. And in that case, this would be like something like R. If R is a partial function between S and T, right? There's a partial function, right? In that case, the domain of R is a subset of S. It's more tolerant. Okay. So you might be thinking about what would be one example where it's both partial and total. Okay. Well, in case there's just a total function, right? So so this will be just a total function, both total and partial. On the other hand, if you actually look at maybe another, how about this one over here? This one here would be, it's actually partial but not total. So there is at least S, which is a member of the first set, S over here, such that the R applied with S undefined. Right? It's a very important visualization you should really have whenever you're thinking about between the two functions. Again, the idea about total function, let me write it down. The idea about total function, sorry, partial function, that's really what I meant to say, beg your pardon. The idea about partial function is more accommodating. On the other hand, the idea about total function over here is more restrictive because it requires the domain of the function to be the entire set from which you're trying to build the relation. All right. Okay, it's very important for you to understand this diagram as well. All right. And let's see some example. This one here, you can see if you look at this just one function, notice one thing here. Here I'm using a membership operator because I'm only supplying just one example function. On the other hand, previously I was supplying one function and two function, right? So that's why I got to use the subset relationship because it's a set of function, right? Just notice the difference there. Right, so here, how do we judge? Well, I already boldface the domain value. You can see the domain for this function here is 2, 3, and 1, which is exactly equal to the first set from which we build the function. And what about this one here? So this one here, you can see it's a partial function, but it's not a total function because in this case, we're missing the value 3 from the domain of this particular function. So that's why it is not a member of, all right? And what about the Ascii syntax? It's easy. It's just total function. Dash dash greater than. All right. It's a very important slide to really brush up about the difference between total function versus a partial function. Later on, when we actually try to model system, very often you have to make a decision, like a design decision, modeling decision, as to whether a variable should be declared as a partial function or a total function. Let's see one such example right away. Right. So you'll be familiar with exactly how to make a decision. Actually, before that, I would like to give you very quick syntax brush up about two very similar applications. They're somehow equivalent to each other, but not always, but very often. We talk about relational image and also function application. Okay, let's talk about these two. This is something important to recall. A function is a relation that satisfies the functional property. However, a relation is not necessarily a function because not necessarily every relation satisfies the functional property, right? It's obvious. Something to recall from earlier. And let's say we have a partial function over here. You can see f is a member of, you can see there's a partial function between these two sets, 1, 2, 3, and also ab, right? So this is definitely a partial function, right? You can see the 3 and 1 here, the domain is a subset of 1, 2, 3, right? Very quick mention, according to what we said earlier in the slides. And now, since f is both a function and a relation, you can apply both the relational image and also the function application. You can either treat f as a relation, in which case you can apply the relational image, or you can treat f as a function, in which case you do the function application, which you do always in the case of mathematics, right? Let's see exactly what I meant. Right, so let's say wearing the hats for relation, we can invoke the relational image, for example, like here, right? So remember for the relational image, it's a square brackets over here, and then the inside the input must be a set over which we want to retrieve the image. And then the result is also a set, right? That's a relational image. You can definitely refer to its definition from earlier slides. And let's say for f, right? So you can see in the case of 3, we're only passing a so-called singleton set just to illustrate the difference. Okay, so only one element in the set. In the case of 3, what will be its image? Well, only a. In this case, because f is also a function, so this resulting set is guaranteed to be a singleton set as well. Otherwise, if from a particular elements, the image is actually a set whose cardinality is larger than 1, in that case, it wouldn't be a function anymore, would it? Because that violates the functional property. Because a domain value is mapped to more than 1 elements. In that case, it will violate. But in this case, it's satisfied. And in the case of image for 1, it will be just b, right? Relational image. And also in the case of 2 2 is not in the domain of this function over here. So that's why its image will just be empty, right? Obvious. Hopefully, so far so good. And let's talk about wearing the hats for function for f, right? It's definitely something I just remarked. You can definitely read it. And let's say if we let f wear the function hat. So in that case, we can do function application. Let's take a look. In that case, we can say f of 3, right? You can see here the input here is only a single element. So it's not relational image anymore. That's why we're using only parentheses as opposed to square brackets over here, right? And the output is going to be a single element. The reason that the reason that the functional application is guaranteed to be a single element is because the functional property tell us that every element in the domain will map to at most one element, right? Every element in the first set S is going to map to at most one. At most one means either 1 or 0. In the case of 1, it's defined. In the case of it's not mapped to anything, in that case it will be undefined. For example, you can see f of 2, because 2 is not in the domain of this particular function, so it will be undefined over here. You can see in the case of a functional application, undefined correspond to the case where you got empty set as a result for relational image, right? So this slide here is not tricky at all. I think it's really to compare and contrast. F being both a function and relation, you may apply either a relational image or functional application, but you got to know exactly the syntax and what the results really mean. All right, it's really important. All right, having known this, let's now try to do one exercise about modeling decision. Let's now do one exercise over here about making a modeling decision. Let's now read through the problem description together, and then I'll give you the some startup artifacts like what's given as assumption, and then I'll let you pause the video and think about how you may model them. Okay. An organization has a system for keeping track of its employees as to where they are on the premises. For example, an employee may be in Zoom A, floor number 23. Obviously, an employee cannot be at 2 locations at the same time, right? It's obvious in reality. To achieve this, each employee is issued with an active badge, which whenever you scan the badge, maybe to the door, it will synchronize the employee's current position to some central database, right? It's a very very often scenario that happens in the real world. So hopefully you can see some more connection between math to the reality. Okay, let's now assume the following. Let's say we got 2 sets over here. Let's say employee is a set containing all the employees currently working for the organization, meaning that if an employee used to be working for the organization, maybe they resign or maybe they got fired, they don't belong to the set anymore, right? Obviously. What about location? Think about location denotes the set of all valid locations in the organization. For example, if there is no floor 24 in the organization as part of their premises, in that case, floor 24 would not be in the location, would not be in the set. Everything contained in the set must be a valid location. All right. So now, what we want, before I actually go through a series of questions to challenge your modeling decision, why don't you think about, based on what we learned so far, we got possibility, we got relation, we got partial function, we got total function, right, between 2 sets. And now we got exactly 2 sets over here. And based on the problem description over here, we may want to have a variable. Let's say the variable is called where is. Where is this particular employee? And now, should that variable declare as a type of a relation between these 2 sets? Or should it be a partial function between these 2 sets? Or should it be a total function between these 2 sets? We got 3 options for you. All right. You can now pause the video and think about your rationale for which one you might go. All right. Assuming that you thought about it, let's now go over the answer. Okay, let's go one by one. It's important not only to know which one should be the appropriate answer, but also what about the other 2? Why are they not the correct answer? You should know them as well. It's equally important. Well, number 1, is it appropriate to model or to formalize such a track functionality? Let's say where is, right? Let's say where is actually a member of the relation between the person and also location. Well, apparently person over here, I really meant to say employee. All right, I'll fix the slides when you download it, right? So whenever you see person for the remaining part of the slide, it's supposed to be employee. All right. So if I say where is a member of the just a member of a relation, well, simply just a relation between employee and also location, would that be appropriate to formulate in this way? Well, the answer is no. Because if this is a relation, what does that mean? That means a person being a domain value may be mapped to more than one locations in the range. So that means we are saying that something like maybe Alan, we are getting a relational image for Alan Alan is actually one part of the domain for the employee, right? And we want to see where Alan is. And and the relation wouldn't forbid you to actually say Alan is in both this location over here and this location here. It's definitely not possible in reality, right? So a relation is not a appropriate formalization or model for this where is variable. It's a very important exercise for us to do. You will actually face this kind of decision very often. Okay, and later on you might even face the decision to say if there's a partial function, for example, should it be injective, should it be surjective, or should it be bijective, right? Let's do some basic one first. All right, anyway, understand why relation is actually not an appropriate model for the where is variable over here for the counter example that we gave. All right, and what about a total function? If I say where is variable is actually again, it should be employee over here. It's a member of all the possible total functions between employee and also location. For you to judge whether or not this modeling decision should be appropriate or valid, you should really think about what is the unique property of a total function. That's something I will give you a little bit hints. All right, it should be no, because if it is a total function, that means every member in the domain, which will be an employee, should be mapped to some value in the range. So in this case, we are saying that every employee should really show up in certain location in the organization's premises. Is that really real? Well, in reality, that's not necessarily the case, right? Think about university. Not necessarily every staff member or every student or every professor might be on the campus, because maybe professors on sabbatical, maybe the student may be on vacation, or etc., right? So that's not realistic to really model the where is as a total function. So this is not appropriate. One example could be, let's say where is over here. If you try that, so Mark in this case over here, so what should be the return value from Mark if Mark is already on vacation? So in this case, if I want to say where is Mark, it should be undefined. And in order to really make it undefined, we need the third kind of function, which will be partial function, right? So finally, the ultimate answer will be a partial function would be the ultimate answer to really choose to model this where is. So it will be a partial function between employee and also location, meaning that not necessarily all the employee should be mapped to a location, not necessarily. But if it really happens that everybody is on the campus or in the organization, that's okay. We allow that possibility, but we definitely don't want to say at any point it's always that everybody is on the location, right? That's different. Right, so this will definitely address the inflexibility of total function, meaning that in the total function, you require everybody to be on one of the locations in the organization at any time. That's not realistic. All right, so this slide contains very important exercises for you to actually apply what we learned mathematically, relation functions, total function, partial function, and apply them into the modeling of real system. And every time you want to make a modeling decision, you have to consider the mathematical property for function relations, etc. Do they really apply to the real scenario that you're really considering? So it's really important to understand if it's not appropriate, what would be the counter example, or what would be the justification, like what I said over here, right? Make sure you understand all the points over here, and then we'll move on to talk about the three special kinds of functions.